All right, guys, welcome back to our recap class. We start now.
Welcome back. This is today we're looking at our lecture 3. So let's just go straight to where we had stopped and then we begin from there. So we were looking at modular universes last time, and we had done we had looked at first, how did we call it, first powering algorithm, which we were using to find the powers of numbers if the powers are higher. And in this algorithm, we said that we were just to square numbers. If the number is n, then we square n, then square n. If you square n, you get n square. Then square the n square to get n raised to 4. Then square that to get n raised to 8, and so on. So this is the algorithm. So you're squaring subsequent numbers. And we looked at examples. So today we'll not go into that. We shall look at another way of finding powers. So before that, we were to look at rings. I was just to define what a ring is. This is where we're supposed to have begun. Now, this set, where m is any integer, m is an integer. It could be 2, could be 3, could be 5, any integer. This set, therefore, is called just a minute. You can see the, it's okay. It's okay. So I was saying that this set, we call it a ring of integers. And what you know that Z is a set of integers. So it's a set comprising of numbers -4, -3, -2, -1, 0, 1, 2, and so on. So this is our set of integers. So our m here is another integer. So I'm multiplying m by z. So when you multiply m by z, you get another set. For instance, if m here is 2, if m is 2, so I'm just multiplying 2 by z. So then you get another set. And this other set that we're getting, therefore, is what we call a ring of integers, mod m. Mod m. So the best will be m. Now, so if m is, let's take m to be 7. If m is 7, for instance, then our set 7z with a set comprising of numbers from 0 all the way up to 6. And that's why I've said that it will go up to m minus 1. M minus 1. So those are the numbers. That means, for instance, if supposing that m is 6, then z of 6 of z, this ring would comprise of numbers 0, 1, 2, all the way up to 5. That is m minus 1. So that would be a set of a ring of integers. So later on, we shall know what a ring is. We shall also see what a group is later on. Now, what is important, therefore, is for us to know how do we add elements, for instance, of this set. How do we add elements of this set? How do we multiply these elements? How do we get the inverses? For instance, what is the inverse of 2? What is the inverse of 5? And so on. That's what is important. And that's what I want to look at using a table. So I want to look at 5z. I want to look at 5z. And we know what elements are in 5z. So 5z has elements from 0 to 4, all the way up to 4. So we want to see how do we add these elements. That's what is important. So I've come up with a table for addition and then a table for multiplication. These tables, we call them Cayley tables. Cayley tables. So if you are doing it for multiplication, then you're getting the Cayley table, multiplicative Cayley table. And if you are doing for addition, then again what you have is additive Cayley table. So let's look at the additive one, where we are adding the elements. So remember, we are doing it mod 5. That means mod 5 means that when you divide a number by 5, what is the remainder? So the remainder is what we are writing. So for instance, 0 plus 1, the answer you get is 1. So 1 divided by 5, the remainder of course will be 1. So this one that I've written there is the remainder. So 0 plus 2, I get 2. 0 plus 3, I get 3. 0 plus 4, and so on. Then let me now add 1 plus 0. I get 1. Then 1 plus 1 gives me 2. 1 plus 2 gives me 3. 1 plus 3 gives me 4. 1 plus 4 gives me 5. But you see 5 is equal to 5. Whenever you get something that is equal to 5 or more, at that point you divide by 5 and write the remainder. So when I got 5, you divide by 5, the remainder will be 0. Now let me now add 2. 2 plus 0 will be 2. 2 plus 1 will be 3. 2 plus 2 will be 4. And 2 plus 3 will be 0. Is that okay? Because that will be the remainder. The answer you get there is 5. 5 divided by 5 gives you a remainder of 0. And then 2 plus 4 is 6. 6 is greater than 5. So we divide by 5 and write the remainder. So that gives us 1. You do the same thing. Let's do it for 4. 4 plus 0 gives us 4. Then 4 plus 1 gives us 0. Then 4 plus 2 gives us 1. And 4 plus 3 gives us 2. And then 4 plus 4 is 3. So that is how you do addition. Let's look for multiplication. See how to do multiplication. It's the same thing. We are doing now mod 5. Mod 5. When you are doing multiplication, I've included 0, but multiplication, there's no need to include 0 because it can never be a ring with a 0. It can never be a group with a 0. So I just included that this 0, but later on we shall see that the 0 is not important for multiplicative group because it will not have an inverse. For it to be a group, it is supposed to have an inverse, but 0 will not have an inverse under multiplication. Now, let's just multiply. 1 times 2 gives us 2. 1 times 3 gives us that. Then 1 times 4 gives us that. Let's multiply by 2. 2 by 1, you get that. 2 by 2 is 4. Then 2 by 3 is 1. Because what you get is 6. Since we are doing it mod 5, we divide by 5 and write the remainder. Is that okay? Then 2 times 4, the remainder will be 3. That's what I wrote. Now, let's look at 3. 3 times 6, no, times 2. The remainder is 1. That's what I wrote. 3 times 3, the remainder is what I'm writing is 4. Then 3 times 4, the remainder will be 2. Now, I've raised a question here. We want to see what is the inverse of these elements. I've already said 0 would not have an inverse. What is an inverse of an element? If I have an element A, B is said to be the inverse of A. Under multiplication, if this product gives us 1, under multiplication, is that okay? So if A times B gives us 1, then we say that B is the inverse of A. We also say that A is the inverse of B. Now, for instance, the inverse of 2, using this Cayley table, under multiplication, the inverse of 2 is 3, because 2 times 3 gave us 1. Is that okay? The inverse of 3 is 2, because you can see 3 times 2 gave us 1. And the inverse of 4 would be 4, because the 4 times 4 gives us 1. So you realize that the only element here that lacks the inverse is 0. That is why I was saying that under multiplication, 0 should not be included in your table, because it makes it not to be a ring. A ring, for something to be a ring or for something to be a group, every element must have an inverse. And so this one now fails to be a ring because of one of the elements here has no inverse. So I'll show you how to remove 0 later on. Yes. Inverse of 2 is 3 in integers mod 5 modulo 5. How would you put that as a statement? Okay, so what I said that an element A is an inverse of B. An element A is an inverse of B mod M if A times B gives us the identity element 1, if A times B gives us 1. Now, so the same thing we are saying, 2 will be the inverse of 3. 2, the inverse of 3, mod 5. Mod 5. since 2 times 3 gives us 1 mod 5. Gives us 1 mod 5. I don't know whether that is, yes. The inverse of 2 is 3. And the reason is 2 times 3 gives us 1 mod 5. Do we know what 1 mod 5 means? 1 mod 5 means that 1 is the remainder when you divide the result by 5. That's what it means. Now, shortly, I'll show you how to get the inverse, because it's not always that you must have this Cayley table to get the inverse. And I already showed you that, but I'll just emphasize. When you're using the Euclid's algorithm, I showed you how to find the Euclid's algorithm. Let me just show you here. I want to get the inverse of 2 mod 5. And I want to use the Euclid's algorithm. So what I do, I want the inverse of what? 2 mod 5. So I ask myself, if 2 are to go into 5, so I'm using, what I'm using here is the division algorithm. What is 5? 5 is the same as 2 goes there twice. Is that okay? And the remainder is what? The remainder is 1. In fact, we've already reached the remainder. That is this is our GCD. Our GCD is 1. So now, we make this one the subject of the formula. And when you make the subject of the formula, what you have is 5 minus 2 multiplied by 2. Is that okay? So from this statement, I'm seeing that the inverse of 2 is negative 2, because, because negative 2 times 2 gives me 1. But what is negative 2 mod 5? Negative 2 mod 5 is the remainder if 5 were to go into negative 2. And I just get that by adding 5 and negative 2. So when I add 5 and negative 2, I get this remainder to be 3. So I find, therefore, that the inverse of 2, therefore, is 3. And how I got 3, I just used the Euclid's algorithm. But whenever I get a minus answer, I make it positive. And so how do I make it positive? I just divide 5 into negative 2. 5 into negative 2. And 5 would go there 0 times. 0 times 5. No, not 0. To go there negative 1 times. Not 0. To go there negative 1 times. Because they're negative 1 times. So that negative 1 times 5, you have negative 5. Negative 5 from negative 2, get 3. Now, but as we proceed, I'll be showing you, because you don't need always to come up with a Cayley table to be able to find the inverse of one element, but you can use the Euclid's algorithm, which we already learned. And then thereafter, we shall again learn another method, which is the Fermat's Little theorem to find the inverse. So let me now show you other examples. I want to look at linear congruences and how to solve a linear congruence. And I've said, consider this linear congruence. A times X is congruent to B mod M, where A, B, and M are integers, and M is greater than 0. What do we mean by a solution to this equation? That's what I began from there. I've said by a solution to this equation 1, we mean an integer, which when multiplied by this A, an integer, let me say that X1 is a solution. Let me say, for example, that X1 is the value of X. You see, when you're asked to solve this, the person telling you to solve this wants you to find X. So supposing you find X to be X1. Supposing you find X to be X1. So when do we say that X1 is a solution? We say that X1 is a solution if x1 multiplied by a minus whatever is here, minus b, if this result can be divided by m, if this result can be divided by m, then we say that x1 is a solution. That's what we mean by a solution. Now, I've also said something here. Note that an equation ax is congruent to b has a solution only if the GCD of a and m divides b. If the GCD of a and m divides b, then this equation has a solution. Otherwise, it does not have. So that is a very important point. That's a very important point, and we need to know that. Because you can be given this equation, and then you'll be struggling to find a solution for it. In fact, when the solution does not exist. So it's good for you, first of all, to find out, before you begin solving it, does it have a solution or doesn't it have a solution? So we've already said that for this equation to have a solution, the GCD of A and M must divide B. The GCD of A and M must divide B. If the GCD does not divide B, and I've already crossed that. Cross that means it does not divide. Is that okay? If the GCD of A and M does not divide B, then this equation has no solution. And so that is what we'll be doing. And so I want to look at the first example. The first example is here. Just a minute. The example is here. Solve the following linear congruences. I have the first equation here. So for me to solve this, now, first of all, the moduli is very small. So since the module is very small, I want first of all to show you so that you understand what we are doing. The module is very small, but then after that, I shall now show you how to solve using the extended Euclid's algorithm that we've just done. When the module is small like this, we can do by trial. We can use trial to find a solution. Because we know what mod 8 means. Mod 8 means that we are trying numbers 0, 1, 2, all the way up to 7. One of these is a solution to this equation. One of these numbers is a solution. So we just try. Which one? We try 0. We want to see whether 0 times 5 will be 3. If 0 times 5 is not 3, we proceed to 1 and try 1 times 5 and see whether it's 3. And then if it's not, we try 2 and so on. So I'm just using trial, first of all, for you to understand what we are doing. Now, so let me do this first one. I said the module is small, so I'll just use trial. I'll use trial. So I want to try numbers from 1. First of all, if I try, I find the GCD. And I want to see if the GCD divides what was it? If it divides 3, because we were given 5x is congruent to 3 mod 8. So we said for this to have a solution, the GCD of 5 and 8 must divide 3. If it does not, then this one has no solution. There's no need of proceeding to find a solution where it does not exist. Is that okay? Yes. So that is the first thing you do. Once you're given this, you test whether it has the GCD, whether the GCD divides that. So I tested that. The GCD of 5 and 8 must divide the number before the mod. The number before the mod was 3. Yes, it must divide the number before the mod. So, yes, the GCD is 1, and 1 divides 3. If the GCD is 1, then it means this system or this equation has one solution. If the GCD is 1, and if that one is dividing the number before the mod, then that system has only one solution. If the GCD is 2, and 2 divides the number before the mod, then that system has 2 solutions. So that means, what that therefore means, that if the GCD divides the number before the mod, then that equation, the number of solutions of that equation equals the GCD. Is that okay? In other words, if the GCD was 2, then that system would have 2 solutions. If the GCD was 3, and 3 divides the number before the mod, then that equation has 3 solutions. If the GCD was 10, and 10 divides the number before the mod, then that system has 10 solutions. Is that okay? So that means you should be able to get the number of solutions. You don't just find one. First of all, you test, you find out how many solutions am I likely to get for this equation. Now, so this one has GCD is 1. 1 divides 3. And therefore, we can say it will have one solution. So, using trial and error, since the mod is 8, we try numbers from 0 to 7 to see which one would satisfy the equation. And the equation was 5x is equivalent to 3 mod 8. So, we want to try 0. 0 times 5 is 0. So, 0 is not equivalent to 3. So, 0 is not a solution, therefore. We try 1 times 5, you get 5. 5 is not equivalent to 3. And therefore, 1 is not a solution. Is that okay? We try 2 times 5, you get 10. Mod 8, 10 mod 8 is 2. Is that okay? 10 mod 8 is 2. 2 is not equivalent to 3, and therefore, this 2 is not a solution. Let's try 3. 3 times that, times 5, will be 15. 15 mod 8 is 7. 7 is not equivalent to 3. Therefore, 3 is not a solution. So we are trying. Let's try 4. 4 times 5 will be 20. 20 mod 8. If 8 were to go into 20, the remainder would be 4. Is that okay? A 4 is not equivalent to 3. Therefore, this 4 is not a solution. We try 5. 5 times 5 would be 25. Mod 8, that is the same as 1. Is that okay? Because 8 going in 25, go there 3 times. Is that okay? Get it 24, the remainder is 1. So we are writing the remainder. And therefore, this 1 is not equivalent to 3, which means 5 is not a solution to this equation. We try 6. 6 times that would be 30. Mod 8, if 8 were to go there, the remainder will be 6. And 6 is not equivalent to 3. That means 6 again is not a solution. We are trying the last number, 7 times that would be 35. 35 mod 8. 8 will go there 4 times because of that 2. Is that okay? The remainder is 3. 3 is equivalent to 3. So that means, therefore, 7 is a solution. We just used trial. Is that okay? We've used trial. Let's do the next question. Trial is good so that we understand what we are doing. Then later on, we look for the other way of doing it. Now, the other question was 6. This is the other question I want to do. This one. 6 is equal to 4 mod 9. Okay, let's see what, so 6 is equivalent, 6x is equivalent to 4 mod 9. So the first thing we do is to find the GCD of 6, 6 and 9. And this GCD is 3. Is that okay? And this 3, we check whether it divides the number before the mod. And we have seen that this 3 cannot divide 4. Since 3 cannot divide 4, this equation has no solution. So you cannot solve it. You cannot find x. Even if you were to try to use trial and error, you see, use trial and error using numbers from 0 to 9 to 8, 0 to 8. You're using numbers from 0 to 8. If you try all these numbers, none of them will give you a solution. None of them is a solution. So this one has no solution. Let's look at the next one. Six x is equal to 8 mod 10. First of all, the GCD of 6 and 10 is 2. Is it? It's 2. And 2 divides 8. So this system or equation has solution. How many solutions? 2. Is that okay? It has 2 solutions. Because we say that the number of solutions, if it has a solution, then how many solutions? They'll be equivalent to the GCD. Is that okay? So it has 2 solutions. We want to find out, using trial, which ones are the solutions. So we are trying numbers from 0 to 9. So let's try 0. 6 times 0. Just a minute. 6 times 0. Somebody who is also. Okay. Okay, so it's okay now. Now, so we try 0. We are trying numbers from 0 to 9. So this will give us 0. And 0, we can see that is not congruent to 8 mod 10. Let's try 1. This is 6. And 6 again is not congruent to 8 mod 10. Let's try 2. That is 12. Mod 10, this is 2. Is that okay? And this is not equivalent to 8. It's not equivalent to 8 mod 10. Let's try 3. This is 18. Mod 10, this will be 8. Is that okay? Which is equal to that. So that means 3 is one of the solutions. And we know we must have 2. Let's try 4. This is 24. Mod 10, this is 4, which is not equivalent to 8. Is that okay? So let me create some space here. Want to try 5. We already have found one solution. So you're looking for the next solution. Let's try 5. 5 times that is 30. Mod 10 is 0. Is that okay? That's true. That 10 goes into 30, the remainder is 0. And this is not equivalent to 8 mod 10. We try 6, and this gives us 36, which is 6, not equivalent to 8. mod 10. You try 7, and this is 42, which is what? 2. Is that okay? Not equivalent to 8. Then let's try 8. This is what? 8. This is 8. 48 mod 10 is 8. And this is equivalent to what? 8 mod 10. So in other words, 8 is another solution. So we don't need to proceed because we only require the 2 solutions, and we order. If you try the other one, it will not be a solution because this is 54. This is 4, which is not equivalent to 8 mod 10. So this system has 2 solutions. And we found that the solutions, therefore, are 3 and 8. I want to try D. I'm again using trial and error. Now, when you're working with the modular arithmetic, we just add, subtract, and multiply the same way we multiply, subtract, and add in other arithmetic. For example, if something is on this side of the equal sign, always cross it to the other side of the equal sign. Just the same way we do with the other calculations. So here we have 3x plus 2 is congruent to 8 mod 10. So the same way I do with other mathematics, I can cross this on the other side of the equal sign. So you have 3x is congruent to 6 mod 10. Is that okay? Once we are here, we test whether it has a solution or not. We test whether it has a solution or not. We find the GCD of 3 and 10, which is 1. Is that okay? And 1 divides 6. 1 divides 6. Therefore, this equation has one solution. We want to try and see. And when you try, you'll find that the solution is 2. Because 2 times 3 will be 6 mod 10. Is that okay? And that is the only solution. You try the rest, they will not accept the solutions. Ajero can say you want to be admitted.
So here we're looking for the GCD of 3 and 10.
Yes, 3 and 10. 3 and 10, because when this one crossed the other side, when the 2 cross the other side, we got 6. Because it becomes minus. Is that okay? Now, so let's look at part E. Part E, and again, I'm just showing you that the same way we do with other mathematics, we do it with the modular arithmetic. There's nothing new here. I'll take 2 the other side of the equal sign and take this negative 3 the other side of the equal sign. And so I have 6x minus 2x is congruent to 5 plus 3 mod 10. And so when you do this, you get 4x is congruent to 8 mod 10. Now, what you realize here is that all the numbers here have a common factor 2. The common factor here is 2. So in this case, where all the numbers, including the moduli, have a common factor, you begin by dividing through by the common factor before you begin solving. So for instance, I may want to divide, if I divide this as same as 2x, is congruent to 4 mod 5. So this tells me, therefore, that this has only one solution. It has one solution here. Because the GCD of 2 and 5 is 1. Is that okay? The GCD of 4 and 5 is 1. Now, ungefanya, if you will have worked this one and that, you would find the GCD to be 2, and that will have said that this system has how many? 2 solutions. So what normally happens is, once you solve this one at the bottom, you can now generalize and get the solution for the original. You can generalize and get the solution for the original equation. And I'll be showing you that as we progress. Now this one, you just multiply by the reciprocal of 2 and 3 on both sides. And so what you get, that is one way. So you multiply, but now what is the reciprocal of 3? You see, when I write 1 out of 3, and somebody else writes this, that is the same thing. That person has written the same thing. Is that okay? So what that therefore means, is that this equation can be written as 2 times the inverse of 3, x is congruent to 4 mod 7. These two mean the same thing. Is that okay? 2 times the inverse of 3 mod 7. So you find out what is the inverse of 3 mod 7. And this is a small number, we can find out what the inverse is. A number which, when multiplied by 3, gives you 1 mod 7. You can just try. You can try numbers from 0 to 6 and see which one gives you 1. If you try 0, 0 times 3 does not give you 1. Does not give you 1. 3 times 1 does not give you 1 mod 7. Is that okay? 3 times 2 does not give you 1. Gives you 6. Is that okay? 3 times 3 gives you 2. Does not give you 1. 3 times 4 gives you 5. Is it 5? Does not give you 1. 3 times 5 gives you 1. 3 times 5 gives you 1. Mod 7. Because 3 times 5 is 15. 7 will go there. The remainder will be 1. Is that okay? So the inverse of 3 is 5. So what therefore that means? What that means, therefore, since we have the inverse, we can rewrite this equation. We have the inverse of 3. So what it means, this equation here can be written as 2 times the inverse of 3 we've just found to be 5. Then times x is congruent to 4 mod 7. Is that okay? Yes. Now, what we then have, this is 10. 10 is bigger than 7. So we reduce it mod 7. When you reduce it mod 7, you get 3. So you can now solve this. You can now solve this. You begin by testing whether it has a solution. Find the GCD of 3 and 7. Is that okay? After finding the GCD of 3 and 7, find it's 1. 1 divides 4. So this system has one solution. Now use trial that we've been using. You try 0, you try 1, it refuses. You try 2, that will give you 6. You try 3, that will give you 2. You try 4. 4 times 3, that is 12. Mod 7, that is 5. Is that okay? You try 5, that's 15. Is that okay? Mod 7, that is 1. You try 6, that is 18. Mod 7, that is 4. Is that okay? So that means 6 is the answer to this system. Is that okay? Now, how we did it, this one, how we did it, we just from here, we knew that what we would do is just rewrite this. We rewrite this. And when you rewrite this, it becomes something like that. So then, since the module is small, we can find the inverse of 3 by checking which numbers from 0 to 6, if multiplied by 3 gives you 1. Because the inverse of A is B, if A times B gives you 1. Is that okay? So you are asking ourselves, which number multiplied by 3 gives us 1? And that number is the inverse, therefore. And the module is small, so we just try 0, try 1, try 2, and so on. And then when we tried, we found 5. Was it 5? To be the inverse of 3. We found it to be 5. So that is why we multiplied this. And this is 10, which is bigger than 7. So again, we reduce it. Then from here, we use our trial and found that the answer was 6. Now let me now show you how to do the same questions without using trial, because sometimes you are given a very big module here. And so if the module is bigger, you can never use trial because you cannot try all the numbers. For instance, if the mod is 60, you cannot try 0, try 1, up to 59. That would be time consuming. Now, so therefore, I show you the other method, the Euclids that we learned. Now you'll go through the workings, like the last one we've just done, the last one we've done, since we are recording, let me just show you the workings so that you can follow the workings later. And of course, I'll share the notes. The working for part A is this one. Then part B, we discovered that the GCD would not divide 4, and therefore that system had no solution. The working for part C is this. Now, this is slightly different from what I did, because what I did when I discovered that there was a common factor, I began by dividing through by the common factor. Then I would go back and find the solution for the original system. But you can still, because you're using trial, you can just try using the old equation. Is that okay? Without dividing through by the common factor. Since we are using trial. But when we go to the method I'm just to show you, the one that does not use trial, that one means it's a must, you must divide through by the common factor for you to solve. Now, the working for part D is here. And then the working for part E follows. And then lastly, the working for part F that was giving us 6 as the answer. And let us see how I did it here. How I did it is slightly different from what I've done. It's the same thing. But now these questions, I said, because they are dealing with we just deal with them the same way we deal with the natural number, the other equations. The way I did it here, I just multiply by 3 on both sides. And when you multiply by 3 on both sides, this is what you get. And then reduce this part mod 7. When you reduce it by mod 7, you come up with this equation. Then from here, we use our trial. This one looks shorter now. Is that okay? But the one that we did in the explanation I did earlier, I thought of how do we rewrite this? That's how I began by thinking. Then I thought this can be written as 2 times the inverse of 3 times x is equivalent to 4 mod 7. From here, then I thought of what is inverse of 3? And we did that. You can go through the workings as we did. But I am seeing the one that I used here is slightly different, but they give the same result. Now, let's now look at how to solve those systems. If the model is large, and look at this equation, the way it's written here. What is here is 1. This one is very interesting because what is there is 1. What that means is that the GCD of 93 and 53 is 1. That 1 means that. It means that. It means the GCD, in fact, is the same thing we were doing earlier. What we were doing earlier was we were writing 1 in terms of the GCD in terms of 93 plus 50. Let me say y. 53x. So we want to write this equation in this form. So when you write it in this form, you'll have found x. When you write this equation in this form, you'll have found x that they want. And to write in this form, use the extended Euclid's algorithm that we did. So what we did is we ask ourselves, how many times does 53 go into 93? So you find that it goes there once, and the remainder is 40. So I'm using the Euclid's algorithm. Then ask myself, what about 40 into 53? And I find that it goes there once, and the remainder is 13. What about 13 into 40? You find it goes there 3 times, and the remainder is 1. What about 1 into 13? Whether it goes there 13 times and the remainder is 0. Once you reach here, we said earlier that then the last non-zero remainder is the GCD. The last non-zero remainder. And that last non-zero remainder is 1. Therefore, is the GCD. So what we are doing, what we've just done, this is the Euclid's algorithm. What we have here is the Euclid's algorithm. We now use the extended Euclid's algorithm. And the extended Euclid's algorithm is now, you make the GCD the subject of the formula. Is that okay? So when you make the GCD the subject of the formula, you're now using the extended Euclid's algorithm, and our GCD is 1. So we make 1 the subject of the formula, and this 1 is the same as 40 minus this. Is that okay? Which is same as 40 minus 13 is here. 13 is here. So the equivalent of 13 is 53 minus 40 multiplied by 1. Then close the bracket and write this 3. So when you open these brackets, you get 40. This minus times 53 gives you minus 53. And remember, there's something outside, which was 3. Just opening the bracket by multiplying by whatever is outside the bracket. So what is outside the bracket is negative 3, yes. Or this one. Yeah, so we're beginning from this equation where the GCD is. And you're making the GCD the subject of the formula. So this one, how do you make 1 to be the only one on the left side? So you have to take this one on the other side. Is that okay? So for 1 to remain alone, you take this other one on the other side. So 1 is left alone. So I've just taken this on the other side. You see it's plus here. When you take it the other side, it becomes minus. That's why I have minus 13 times 3. Then from there, you see I have to replace all these remainders in the equation. Whenever they appear, whenever these remainders appear, I replace them. So I've replaced the first remainder. Now I come up with this equation. This equation has the next remainder, 13. It's here. I'm replacing going up. Replacing going up. So when I replace going up, what is 13? 13 to go on one side alone. I have to take this on the other side. So that is 53 minus this. That's what I have. So 13, I substitute by, it is equivalent, which is 53 minus 40 multiplied by 1. Then this 3 is this. Now, to open this bracket, I have to multiply by whatever is outside the bracket. What is outside the bracket is negative 3. Negative 3, so 53 times negative 3. And then negative 40 times negative 3 gives you plus 40 times 3. Is that okay? Because minus times minus is positive. At this point, you collect the like terms, and I'm seeing this and these like terms. And this one, this 40 is just like somebody giving you 40 times 1. And so then I have 40 times 3. And I'm combining these two. So this is the same as 40. Whatever is inside the bracket is 1 plus 3, which is 4. So then this gives me 40 times 4. Then minus 53 times 3. Now I had replaced my remainder 13. So now I replace my remainder 40. So where it is, I replace it. So I have it here, 40. I have it there. But its equivalent, I take it on the other side. Its equivalent is 90 minus 53 times 1. Yes? Or 93. 93 minus 53 times 1 multiplied by 4. Is it? By 4. Then minus 53 multiplied by 3. So I create some space here. Create some space here under it. So I just want to open this bracket using 4, which is outside. And so this gives me 93 times 4. And this one is negative 53 times 4. I've already opened this bracket. Then there is minus 53 times 3. At this point, I collect like terms. And I can see 53s. So this gives me 93 times 4. 53 have minuses. Whatever is inside the bracket is 4 plus 7. Which is, no, 3 plus 4, which is 7. That's what I get. Now, so what was the question? The question was, find the value of x. Find the value of x. That was the question. And what is interesting is this value here, 1. And it's what we have here. It's what we have here. Also, what we've been solving. And we found that 1 is equal to this. So that means, therefore, the number which when multiplied by 53 to give you 1 is this -7. Is -7. Yeah, what we've been solving is this. We've been solving and we've been writing. We began by making 1 the subject of the formula. And so we found that 1 as the subject of the formula is the same as 93 times 4, then minus 53, but we can write even plus 53, and the minus is there. There's no problem. The same thing. Is that okay? Good. Because why I'm doing that is that 53 did not have a minus. So what I know is that if A is positive, and I'm multiplying A times B to get minus AB, if A is positive, then B is the one that has a minus. Is that okay? Yes. If A is positive, and if the product of A times B is negative, then it means that B is the one that has that minus. So that is, our 53 here is positive, but what we are getting here is negative 53 times 7. So it means the one carrying the negative sign is that 7. Is that okay? So what that then means, what we've just written here, what it means is that the number that can be multiplied by 53 to give us 1 is -7. It's -7. But what is -7 mod 93? Because it's -7 mod 93. I want to write it in positive, as a positive number. So the way we've been doing from the beginning of this class, what I was doing, I was just adding the mod to this number. When you do that, you get 86 as the value of x. 86. Now, you see this question, we have used this question to do several things. One, we've used this equation to find the value of x. And two, because what was coming before the mod was 1, we've also used this equation to find the inverse of 53. So the inverse of 53 is there 56. Because it's 53 that when you multiply by, is 86, which when multiplied by 53 gives you 1. So the inverse of 53 is 86. Is that okay? Yes. I want to take another question. I want to look at the next question. See what to do. So I got 86 as the answer there. Now let's do this. This one is interesting. There were number coming before the mod is not 1. So what that therefore means is that what we are getting is not the inverse of 7. Is that okay? What we are getting is not the inverse of 7. Now, we want to find x. We use extended Euclid's algorithm. But we began by Euclid's algorithm. We want to find, so ignore this one first of all. Ignore the number before the mod first of all. Let's concentrate on these two numbers. Find the GCD by the Euclid's algorithm. Ask ourselves 7 into 19, because they are twice. The remainder is 5. 5 into 7, because they are once. The remainder is 2. 2 into 5, because they are twice. The remainder is 1. 1 into 2, because they are twice. The remainder is 0. So therefore, this is the GCD. This is the GCD. Make the GCD the subject of the formula. Make the GCD the subject of the formula. So our GCD is 1. To make it the subject, we have to take this on the other side to be 5 minus 2 multiplied by 2. Substitute this 2, our remainder, substitute the remainder is going up. Is that okay? So this is 5. This remainder is 2. But the equivalent of 2 is 7 minus this. 7 minus 5 multiplied by 1. Then multiply this 2. This is 5 minus 7 multiplied by 2 plus 5 multiplied by 2. The plus is coming as a result of minus times minus. Collecting like terms, you have 5 multiplied by 3 minus 7 multiplied by 2. If you collect like terms, replace the next remainder, which is 5. So this will be the same as, instead of 5, write the equivalent, which is 19 minus 7 multiplied by 2. Then multiply this 3. Then minus 7 multiplied by 2. Open the brackets. When you do that, you get 19 multiplied by 3 and get 7 multiplied by 6 and then get negative 7 multiplied by 2. Is that okay? This gives you collect like terms. First of all, you have 19 multiplied by 3, and then you have 7 multiplied by negative 8. Seven multiplied by negative 8. 6 minus 2. Negative 6 minus 2. Is that okay? What do we want? What we wanted was this. What do we have? Let me just write what we have. Create some space and write what we have. And then relate the two. What we have is, what we just obtained is 1 is equivalent to 19 multiplied by 3 plus 7 multiplied by negative 8. But what we wanted was this. What we wanted was 13. We wanted 13 to be equivalent to 7 times x. 7 times x plus 19. This is 19 multiply by something, I call it y. That's what we wanted. But what we have instead is this. So what this then tells us, for us to move from this equation, to get this equation, we need to multiply the first equation by 13. Is that okay? For us to move from this to get this, we have to multiply the first equation by 13. So multiply equation 1 by 13. What do you get when you do that? When you multiply by 13? Now, I don't really multiply inside the brackets, actually. I just multiply inside the bracket. I want to maintain the numbers. I want to maintain the numbers 19 and 7. So I multiply inside the bracket. So that means this one times 13, this one times 13, I have 13. And then 19, this is 3 times 13. And then plus 7 multiplied by -8 times 13. And I have to remember I'm working mod 19. I'm working mod 19. So every time a number is bigger than 19, I'll reduce it to mod 19. So what I get here is 13 is equals to 19. What is yes 39? Reduce it to mod 19. And you have what? You have 1, is it? What is 19 times 19? 38. So you have 1. The remainder. Is that okay? Now, the last time I told you when you are doing this, you don't need to struggle with your calculator. When you are doing this, once this number is bigger, is approaching, this number is approaching 19, just make it negative. Like this, like what I have inside this bracket is 3 times -6. This 13 is -6. Mod 19. Is that okay? 13 and -6 are equivalent, are congruent. And so this gives you -18 mod 19. And whenever this is negative, as we've been doing it from the start, we've just been adding this and this to get a positive number. Add 19 and this to get a positive number, you get 1. Yes? After multiplying here. Yes, just before that, what we said, every time I'm doing this multiplication, I want to deal with the smaller numbers. So when you're dealing with the smaller numbers, it becomes easier for you. So when 13 is very huge. Because it's very close to 19, I just make it negative. Just make it negative by subtracting 19 from it. When you subtract 19 from it, you get -6. So what I have here is 3 times -6, which is -18. When I get -18 mod 19, I want to change this number back to positive. So I'm asking myself, if 19 were to go here into -18, what will be the remainder? The easiest way to do that is just to add this 19 and -18. Is that okay? Now, if it's very huge, for instance, let me talk of, supposing I got, this is a very small number, it's -18. Supposing it was -200 mod 19. I'll add 19 to it, add 19 to it, add 19 to it, add 19, add 19 until I get a smaller positive number. Is that okay? Yes. Until I get a smaller positive number. Or alternatively, you are dividing. For instance, if 19 were to go into -18, we go there -1 times. 19 into negative 18, go there negative 1 times, and the remainder will be 1. Now, so let's just come back to where we were. There is this. So this is where we are. What we are doing, we're multiplying by 13, equation 1 by 13, to get equation 2. And then you compare equation 1 and 2. So just multiply 13 times 3, and we found it to be 1. In fact, this one is, there's no problem. There's no problem. The problem is only what I multiply by 7, because I want to get x. This one you can write anything, you can write even 39 here, there's no problem. Is that okay? Yes, it will go twice and the remainder is 1. But yes, but now I'm interested with the value of x. I'm interested with what is multiplied by 7. So whatever is multiplied by 19, I have no problem with that. You can reduce it or you can leave it as huge as it is. Is that okay? Because what we want is the value of x. That is what I'm interested in. And the value of x is what is multiplied by 7. So this is now my interest. So what is it? This is where I'm interested. Okay, you can multiply and get a negative number. Or alternatively, I want to reduce this 13 mod 19 so that I have negative 8 times negative 6. Is that okay? These are smaller numbers. So that this gives you positive 40. Then ask myself, 19 goes there many times? And the remainder will be 10. The remainder will be 10. Is that okay? You see, if you're using a calculator, especially you're using your phone, let's just go to our phone and see how to do it. And I just want to show you how to use your phone so that you don't erase what you have. So I'm on my calculator using my phone. So I multiply, what is it? It is 48. 48. I divide that by 19. What have you found? You found 2.5. Is that okay? So now I just change that division sign to negative. Change that division sign to negative. If your calculator can do that, like mine, I just click on the division sign. And then it gives us, it highlights it. So I now change it to negative. And then click to 19, if your calculator allows. And then there's a tick down there, is it? If you click on the tick, it gives you an opportunity to type the next number. So I now click times. And when you click times, then times 2, because we discovered 19 had gone into 48 2 times. So now just put that 2. What do you have? Yeah? You have 2, is that okay? You have 10. Okay, your calculator may not be doing what I'm doing. Let's do it again. Let's do it using another way. 48, divide that by 19. You have 2 point something. Now I write that 2 somewhere. And then you change, now delete 19, delete 19, delete the division. I've deleted 19 and division, is that okay? Then write minus. 48 is still there. Write minus. Sharon wants to be admitted. Sharon wants to be admitted. So 48, I've written the minus. Now that minus, after minus, write the 19 and the 2 that you had written somewhere. And you have 10. Is that okay? Yeah? That's the easiest way to do that. Now let's come back to the question. The question wanted us to find x. X was the number multiplied by 7. From what we now have, our X is 10. From what we now have here, our X is 10, the number multiplied by 7. I want to look at the other question, and just once, then we move to another thing. So the workings are here because we are recording. Somebody can look at the working later. The working begins from there, and then we move. Then we come up to 10 as our final answer. Now let's look at this question 35. We said first of all, once you're given this question, you try and see whether it has a solution or not. You only proceed if it has a solution. Is that okay? Yes. So how do we test? We find the GCD and see what the GCD divides a number just before the mod. So when I did the GCD, I found to be 13. And of course, 13 cannot divide it 27. Therefore, this system or this equation has no solution. That's the end of that. So we then proceed the next question, because this one we found that we don't need to solve it. We cannot get a solution to it. We come to this other one. And there's something I want to show you here. I'd already said that you find the GCD, and if the GCD divides this number, then the equation has solution. How many solutions? The number of solutions equals to the GCD. Is that okay? The number of solutions equals to GCD. So this said the GCD is 3. 3 divides 9. And so the equation has 3 solutions. The equation has 3 solutions. So you now proceed to get the 3 solutions. I want to show you how to do that. When the GCD is 3, and 3 divides this number, that it means this number 15, 9, and 57 have 3 as a common factor. Have 3 as a common factor. When you were doing the previous example, I said that if there is a common factor, you divide it through by the common factor first of all, before solving. So now let's divide it through by the common factor 3. So when you divide this equation by the common factor 3, this is what you arrive at. You divide everything by 3. 15 by 3 gives you 5. 9 by 3 gives you 3. 57 by 3 gives you 19. Now, this one, the GCD is 1. And 1 still divides that. So, of course, it has a solution. This one has one solution. After getting this one solution, you use it to get the solution to the original equation. Is that okay? Now, how do we find a solution for this equation 2? We just do the same way we've done before, using the Euclid's algorithm. You have 19 and 5. 5 into 19, 3 times, the remainder is 4. 4 into 5, once, the remainder is 1. Then 1 into 4, 4 times, the remainder is 0. Now reverse, using the extended Euclid's algorithm, make 1 the subject, and you have this. When you make 1 the subject of the formula. Then substitute for 4. The equivalent of 4 is 19 minus 5 multiplied by 3. Substitute where 4 is. Where 4 is, write the equivalent. And of course, this one is is 1 here. Then open the bracket, you have that. Collect like terms. This 5 times 3 times 5 times 1 gives you 5 times 4. And then 19, this negative 19 times 1 is the same as 19 times -1. That's what I wrote. Now, so what this means, therefore, is that we have a solution for this system. Just a bit, we need to modify, because what we have here, what we just obtained is that 1 is equivalent to 19 times -1 plus 5 times -4. But what we want, equation 2 is saying that 3 should be the same as 19 times y plus 5 times x. That's what equation 2 is saying. Is that okay? Question 2 is saying that. So I want to use question 3. Want to work on this until you obtain this. Until you obtain this. So that means you multiply question 3 by 3. Multiply equation 3 by 3. I'm doing that because I just want these two numbers to be equal. Is that okay? Yes, that's why I multiply that one by 3. So when I multiply it by 3, equation 3 by 3, the left side has a 3, and the right side has 19. -1 times 3 gives you -3. Then plus 5. 4 times 3 gives you 12. Mod 19. Mod 19. We have obtained the value of x. We have obtained the value of x. A number which, when multiplied by 5, gives you 3. A number which, when multiplied by 5, gives you 3 is 12. So that is x. This system had 3 solutions. The first solution, I call it x1, is 12, which we've just found. How do we get the other solutions? The other 2 solutions. The other 2 solutions you get by taking the initial solution. The initial solution x1 plus this new mod, which is 19, multiplied by t, where t is an integer. T is an integer. Is that okay? Which integer is that? We had 3 solutions. So t will be 1 or 2. Is that okay? That case. Or if you want, just say that x will be given by x1 plus this. So let's say then where t is 0, 1, 2. T is 0, 1, 2. I've said 0, 1, 2 because we want 3 solutions. Is that okay? The first solution is when t is 0. The second solution is when t is 1. And the third solution is when t is 2. When t is 0, let me just write this again. Let me just write here. Just properly. So we write properly. What is x1? So x is x1. X1 is 12 plus 19t. So when t is 0, then what is x? 12. When t is 1, 12 is 31. Is that okay? When t is 2, 50. Because that would be That would be 38 plus 12, which is 50. You know what I've just done? This method is a general method of getting all the solutions. Supposing there were 90 solutions, you just use this general method. You say where x, if it's 90 solutions, then x should be 0, 1, 2, up to 89. Is that okay? 90 solutions. That to be 100 solutions, then 80 will be 0, 1, up to 90, 99. But for these smaller solutions, what we've just done, in reality, what we've just done, after getting x1, to get the next solution, you take this 12 plus the mod, the new mod, which was 19, plus the new mod, which was 19. Is that okay? 12 plus 19. We give it 31. Is that okay? Yeah? Then to get the next solution is that 1 plus that new mod, and you get 50. Is that okay? So just adding the new mod first time, second time, and you have the three solutions. What's the first solution? The first solution we found, the first solution was 12. So the second solution will be 12 plus the new mod, which is 31. The new mod we found, this is the new mod we are referring to after dividing by the common factor. Then the third solution is just this one plus 19, and that gives you 50. Is that okay? That is if you are dealing with very few solutions. But if you are dealing with several solutions, it's good to come up with an equation. It's good to come up with an equation plus 19t, where t, you define t is from 0 to what? Yes, m minus 1, where m is the new mod, m minus 1. Now, so the working is here. The working is here. I've shown the working, and I've shown up to where I have those three solutions. X1 being 12, the other one 31, the other one 40, 50. And I defined my n to be 0, 1, and 2. Now, I think I should take another example just like that, where we have several solutions. The GCD of this number and this, the GCD of this number and this, I discovered it is 4. When you do it, you find it's 4. And 4 divides this number. And 4 divides this number. Is that okay? Yes. So that means this equation has 4 solutions. Is that okay? Good. The first thing we do, divide the entire equation by the GCD. And you have this. When you divide it by the GCD, the entire equation. Now, from there, what follows, we know it. What follows is to use the Euclid's algorithm on this equation 3. Use Euclid's algorithm on this equation 3. Find the GCD of equation 3, which is 1. And then using the extended Euclid's algorithm, make 1 the subject of the formula, and you know how to do that. You arrive at this. This is where I want to begin from. Also, you know how to arrive there. Now, comparing this, I compare this with I compare it to, just a minute, clear that. I compare it to equation 3. Equation 3 says, there's 71. 71 should be written in terms of 364x plus 765y. Is that okay? Yes. But what do we have? What do we have? What do we have? I've written the whole thing here. What we have is this. But what we are supposed to get is that. That means this equation should be multiplied by 71. So when you multiply by 71, you get this. And then here by 71, you get this. What is our mod? Just go to where the mod is. The mod was 3. The new mod. The new mod was at the summit. 360? 765. Or 765, yes. So that's what I did. That's what I did. Let me show you how the mod is 765. So somebody might be wondering how we got 401. Just multiplying negative 59 times 71. What do you get when you multiply just the way they are? Using a calculator, you get what? 4189. And the mod is what? 765. So we ask ourselves, if 765 were to go here, what would be the remainder? So the easiest way is for me to take this number and divide by 765. What do you get? Negative 35. No, just divide that by 765. Just divide this. What do you get? You get negative. Just the number before the decimal, 5. So that means, therefore, that 765 will go into this number negative 6 times. Yes, but I just ignore the point and add negative 1 to the result before the decimal. For instance, let me show you what I'm doing. Let me show you, because I'm showing you how to use your calculator so that it becomes easier. So for instance, somebody is asking me how many times would 8 go into, no, just a minute, what have I written? How many times would 8 go into negative 9? Somebody is asking me that. So I'm using my calculator there. I'm dividing negative 9 by 8. What do you get? The number before the decimal. Negative 1. And therefore I say confidently that 8 goes into negative 8, negative 2 times. I added negative 1 to what I had gotten. So that when I multiply these two, I get negative what? 16. When I subtract, I get what? I get 7. So the remainder is 7. Is that okay? Yes. So if somebody asks me, how many times does 2 go into negative 3? I just divide 2 into negative 3. And again, negative 1 point something. So this negative 1 is the one I'm interested in. I add another negative 1 to it. And I say it goes there negative 2 times. Is that okay? Yes. I'm not interested with the decimal there. I'm interested with the number it goes there. So that means it will go there negative 2 times. Not negative 1. It will go there negative 2 times. Yes. So that when you multiply this, you get negative 4. When you subtract, the remainder is 1. The remainder is 1. Is that okay? Yes. So that's what we are doing here. That's what we are doing. Let me just clear this and then I continue explaining. So what we were doing, we're asking ourselves, how did they get this? So I then said, I multiplied 71 by 15, negative 59. The answer I got was negative. I divided by the remainder, 765. No, the mod, 765. That gives you the remainder of 4. Now, there were 4 solutions. Is that okay? 4 solutions. So they're taken care of. The first solution is when n is 0. Then when n is what? 1. When n is 2. When n is 3, you get the 4 solutions. So all of them are here. All the 4 solutions are there. I think we can have a break of some 10 minutes. It's okay. Then we resume at after 10 minutes. Now, so welcome back, want to continue. Okay, sorry for that. Welcome back. Want to use this session of about 1 hour to do some revision questions where we'll be discussing questions. So I just give you some questions, then you discuss in your groups and write the answers. For those who are online, you write the answer in your group. Then after that, if the answers are different, then that means we'll have to discuss to see what the right answer is. And one person will be leading us through that discussion. The person who will have gotten the answer correct. Now, so we'll just take simple questions just to see whether we remember what we've learned. So the first question that I want us to look at, I want us to find the value of x that is congruent to 3 mod 9. I want us to find the value of x. So you get some time, you do that question, then I'll mute myself as you do that question. Then after you've done, I unmute and then we discuss. If someone is online and he has the answer, can write under the chat. Somebody who's online can write under the chat so that we can all see the answer. Now, we used trial and error. Is that okay? Now, you're supposed to also know to use the other one. It was 2x is congruent to 3 mod 9. Now, so we test the GCD of 2 and 9, and this is 1. Is that okay? And 1 divides 3. Is that okay? Therefore, we have a solution. We have one solution. Is that okay? So since we have one solution, we use the Euclidean algorithm using Euclidean algorithm. 9, the same as 4 times 3 times 2 plus 1. Is that okay? So in fact, this Euclidean algorithm has only one step, because the next step will give us remainder of 0. So that means we just reverse this equation now. Reverse and make 1 the subject of the formula. So that 1 becomes 9 minus 4 multiplied by 2. So in other words, but what we want is 3 here. What we want is 3. One the subject. One the subject. Now, so 1 you see this the GCD. So we make the GCD the subject of the formula. So the GCD, which is 1, equals to this. We didn't have several steps, so just one step. So just make the GCD the subject, and we have this. Now, what we want is 3. What we have is 1. Is that okay? Yeah. So you multiply this equation by 3. Because we want a 3, but we have a 1. So multiply this equation by 3, you'll get 3 is congruent to 9 multiplied by 3, which is congruent to plus 4 multiplied by 3, 2. We are doing this mod 9. Mod 9. What you're interested in is what is multiplied by 2. What is multiplied by 2? Just a minute, there's a minus here. There's a minus there. Is that okay? Yes. Minus 4 times 3. Mod 9. This negative 12 is what is multiplied by 2, and that's what we want. What is multiplied by 2? So negative 12 is x, so x is negative 12. But it's negative 12 mod 9. So as I said earlier, you just divide 9 into negative 12. The answer you get, the whole number you get, add negative 1. Is that okay? So that means 9 goes in negative 12, negative 2. Is that okay? Negative 2. So what will be the remainder? So that means, or alternatively, just add 9 to negative 12 several times until you get a positive answer. Add 9 to negative 12 several times until you get a positive answer. So when I add 9 to negative 12 once, I get negative 3. When I add 9 the second time, I have 6. Is that okay? Yes. So x is 6. Which is 6. So that's how you use the Euclidean algorithm. That's how you use the Euclidean algorithm. And I know you use the trial and error. Trial and error works only in this case where you have a smaller module. But if you're given a larger one, the only method that will work at this point is the Euclidean algorithm. Yes, that is the only one. Let me now give you one that has slightly larger mode so that you are forced to use the Euclidean algorithm. Now you try that. Find the value of x. Again, this one has very few steps. Oh, yes. Yes. So the answer should be this. Yes. So that you are going to contribute. To what? Begin from the first term so that we see how we arrive there. Oh, that is the first example. Yes, okay. First of all, before that, just use the division algorithm first of all, 9 and 2. Oh, so the first number there is 9. What is your question? Okay, so she's asking the first example. The first example where we had one, we wrote 1 as 9 minus 4 multiplied by 2. Then she's asking how we arrived at what? 3. Yeah, the question that we were given was 2x is 3 congruent to 3 mod 9. And we said what this means, what this question means is that 3 can be written in terms of 2 and 9 as 2x plus 9y. This equation means that. Yes. So when you are writing, so we are assuming that 3 is the GCD of something or some. So for instance, when you are writing the GCD in terms of the 2 numbers given to us. So in this case, the 2 numbers given to us are 2 and 9. So we are writing 3 in terms of 2 and 9. So this question is telling us that in terms of 2 and 9, 3 is the same as 2x plus 9 something, 9y. But now we are interested in finding the x. And so that is now when we come from this question, from this equation you've written, what we have is 1 is equivalent to 9 times something minus 4y, which can also be written as 1 is the same as 9 plus 4 multiplied by -2. Let's say it's 4 in terms of 2. Supposed to be, just a minute. Supposed to be 2 minus 4. So we want this equation to be like this. So we want a 3 here. To get a 3 here, we multiply the entire equation by 3. So when you multiply the entire equation by 3, you get 3 is 9 multiplied by 3 plus 2 multiplied by -12. It is this -12 that we're reducing to mod 9. And it gave us 6. Yes, so when you reduce -12 to mod 9, it gives you 6. So that is just clarification on the first question we did. Now back to our second question. What was the answer? The second question. I said that I've already given the answer. So I just want somebody who has gotten that answer to show us the what is. I've said the answer is 19. Anybody was got 19? Let's have somebody who was done it, or who is on the way, still doing it, and is stuck somewhere. And we begin from there, where the person is stuck, and see how to move from there. It's always good to get stuck. When you get stuck, and then somebody tells you, this is why you are stuck. Next time, you always, when you reach there, you can see how to maneuver from there. So we can have either somebody who has done it or somebody who is stuck. Also, it's either we are stuck or we have done it, is it? From behind, let's have our friend at the back. Are you stuck or you've done the answer? You have the answer. You? Yeah, you're doing. So you're not stuck and not yet. It's okay. And my friend this friend of mine here, are you stuck or you have the answer? You're still doing it. It's okay. Battery. Battery, sorry. Yeah. Okay, anyone with an answer? Or anyone who is stuck? So either you're stuck or you have an answer. Anyone who is stuck, you tell us where you're stuck so that we see how to get out of that. The two ladies, yes? You're stuck on number 3. And number 2, you have the answer. 19. Come on, show us. Yes. Or you can come and write it here. Let me just, you have the question, is that okay? So I can erase so that she just does it from here. So you can just write here. Yes, just see the hand.
Naandika swali. Nawapikia. So this is the question. So assuming this is our A, this is our B, and this is our M, we need to find the GCD of A, M, such that it can divide B. So you Euclid. Okay, so GCD of GCD of 13 and 23. So start with 23. How many times does 13 go into 23? Once, with a remainder of the remainder of 10. Sindio? Okay. How do you scroll?
It's just one page.
Oh, it's one page. Okay. Oh. Oh,
Okay. Oh, sorry. So No.
Ngoja.
Yeah, or you can pages. Check it, but explanation of what is like.
Yes, sir. Create several pages. Just to go back to Word.
You have notebook.
I was using Word. Using this. So create several pages here. How do you do it?
Undo.
Okay, we can just write small.
Yeah, just write. What was it? This one.
This is what.
So only,
Take it
yeah,
from the
just
top.
like, and then just fill.
GCD of 13 and 23. Okay. So how many times does 13 go into 23? That's 1. The remainder of 10. Given 13, how many times does 10 go into 13? That's 1. The remainder of 3. Given 10, how many times does 3 go into 10? That is 3. The remainder of 1. Given 3, sorry. How many times does 1 go into 3? 3 times the remainder of 0. So this becomes our GCD. Then we now set reverse in the extended something. So we make 1 the subject. So if we were to take this 1, make it cross over to this side, making 1 the subject, that would be 10 minus 3, 3. Okay, so we write this remainder as, how do I see it? Okay, rudi huko nyuma, you see on top this thing over here. Now make this 3 the subject. So that becomes 10. Okay, minus making 3 the subject, that is 13 minus 10 times 3. Okay, then go on and open 13 into 3 minus plus 10 into 3. Like terms, this and this, that gives us 10, 4 minus 13 into 3. Our previous remainder was 10, so make this the subject in this case, and then write it as an expression of this. So that becomes 23 minus 13 times 4 minus 13 into 3. Sindio? Then that becomes 23 into 4 equal 1 minus 13 into 4 minus 13 into 3. Like terms together. So that becomes, that is 23, 4 minus 13 into 7. So that means that 1 can be expressed this way. Cindy? That's true. Yeah. Yes. So remember our equation. Remember our equation, which was 13x is that one, 2. Yeah. So that was our equation, Cindy. So we want to write this. unaona tukifanya simultaneous equations, the way we want to make this part, this one, this the left hand side be equals to the same. So that's what we're doing. So assuming that this is 23y minus 13x, we now multiply by 13. Iko kwa akili lakini sijui kusema vizuri. We multiply by 13, si ndio? So it becomes, yeah, the left hand side. So it gives us 13 is equals to 23, 4. So this is y, si ndio? Times 13. So we can change this to be an addition and then up equal minus, si ndio? Because, okay, we can do that because I'm assuming because 13x is already positive. So it becomes plus 13 into -7 times 13. That's correct. Times 13. So, we were using 13. No, that's even, no, I've already misled you. I've misled you because, it's okay.
It was 17.
It was 17, not
It was
13.
17.
The equation was 17. So you're supposed, yeah. Just assume we were correct. The process is the same. The numbers are different. Okay. So that's 17. So it becomes 23 into 4 times 17 plus 13 into -7 times 17. Okay. So, okay. Still, let's move solve your part because we're interested in the x. Interested. Yeah, interested in the x. So this, okay, this will give us -19 with 23. 119, sorry, with 23. So how many, okay, venye nimelewa, given negative, I'm doing it on paper, but given -119, how many times, number line, how many times are we moving until we get to a positive number? You get, like assuming you have a number line and you're at -19 and you're adding 23. So how many times are you moving until you get to the positive number? Now that's how you're going to do this commode over here. So that gives you 17. That gives you 19. So if you were to do, that means.
In other words, you divide this 23 into
Yeah.
-119. The answer you get on the left side of the decimal.
Yeah.
Add -1.
-1, yeah. Yes.
That is one way.
That's one way.
So what do you get when you do that? -119 divided by 23, what do you get? You get negative what? Just on your calculator. Just do it on your calculator. You get -5. That is -119 divided by 23.
Yeah.
You get negative point something, yeah?
Yeah.
So that -5 add -1. That means 23 goes into -119 -6 times. So what we then do, that -6 times 23, add it to this,
Yeah.
get the remainder.
19.
Which is what?
19.
19, huh?
Yeah.
Yes. That is one way. The other option that we did, we said, since this number, this 17, is very close to 23, make it negative what? 6. Is it 17 mod 23 is congruent to, just subtract this 23 from 17. What do you get?
6. 23 minus 17.
Get -6.
Yeah.
Yes. So negative 6 times negative 7, positive 42, mod 23. So you're asking ourselves, if 23 were to go into 42, what will be the remainder? We'll get 19. Is that okay? And you say, I said, if this number is becoming too huge, always make it smaller. That is why I do this mod 23, and you said it will be 6 negative. Negative 6. Is that okay? So that is 42. 42, 23 into 42. The remainder is 19. That's another way.
Question. If I was to multiply this 13 times 19,
Yes.
is it supposed to?
The answer would be, if you divide that result by 23, the remainder will be 17.
17.
That is what the question is saying. The question is you are finding the value of x. Just try what she's saying. She's saying the question we've been given is 13 times x. We found our x to be 19. Is that okay?
Yes.
So let's multiply 19 by 13. Then divide by 23 and see whether we get a remainder of 17. That is what she's asking.
So that's when you're finding the x, you're using smaller figures, and then when you're done, you convert it to the actual equation.
The same answer, because if, for example, this 13, if I was to convert to a smaller number, the way she's saying, I would get negative 10. And then this 19, I would get negative 4. Is it? If I subtract 13 minus, no, it's 13 minus 23. I'd get negative 10. Then the x is found to be 19. Convert to a smaller number, that will be negative 4. So negative 4 times 10 times negative 10. Is that okay? Negative 4 times negative 10, that is 40. Positive. So if 23 were to go into 40, the remainder will be 17.
Yeah.
The remainder will be 17. No. It's always the remainder. So there's the remainder. What is there is always the remainder. So you can always prove, if you are right, you can always prove to know that the question is, the answer is what is right. By just multiply x by 13, then divide by 23. See if your remainder is 17. You can always prove. Okay, so that is how we do that question 3. Then question 2. That was question 2. So question 3, they say they were stuck. Some of them that is not stuck. We are all in agreement that is how question 2 was supposed to be done. Is that okay? So then we proceed to question 3. Okay, let's have somebody leading us in question 3. What was the question? Let me write it here. It was what? What was the question? Question 3. Hmm? 15.
2025. 19.
And we said the answer was 45. So you see this question is the same as somebody asking you, what will be the remainder if 90 were to go into this number? Because we said whenever we write A mod M, it means A is the remainder, is always the remainder when X is divided by M. When X is divided by M, A is the remainder. So what the person is asking us, find the remainder of this number. So this number should be written, you see the remainder should always be less than the divisor. The divisor is 5. We are dividing a number by 5. The remainder is supposed to be less than 5. Is that okay? If you are dividing a number by 4, the remainder is supposed to be less than 4. Is that okay? So if you are dividing by 90, this person is asking us to get a number that remains. So that number should be less than 90. It can never be more than 90. So this one, you would use the first powering algorithm we learned about. Yes, the first powering algorithm that we learned about. So where let me just take it. Let me do it here. We would say 15 raised to 1 is 15. 15 raised to 2, and just use your calculator. 15 raised to 2 is what? Is 225. Yes, but now we want to write the remainder if we were to multiply by 90. Yes, that's what we write. So we just take 225 divided by 90, get 2.5. So that 2 is what we're interested in. Is that okay? So then, what is 225 minus 90 times that 2? So we find a remainder of 45 here. Then what about 15 raised to 4? We are squaring the previous answer. So we've squared this, we got this. Now we square this. Is the same as 45 squared. When you square this equation 2. So we've squared. When you square this, you get 15 raised to 4. When you square this, is 45 squared. So what is 45 squared? You get 2025. Is that okay? That 2025 divided by 90, one the remainder. So it goes that in 2 times. So what is the remainder? So the remainder is what? How many times did you go there? 225. It was 2025 divided by 90. It went there 22 times. 22, is that okay? So now let's take 2025 minus 90 multiplied by that 22. and you get a remainder of 45. Yes, we want the remainder. Because that was 2025. When we squared 45, we got 2025. So then we divided by 90. It went there 2 times. So now to find the remainder, we take that 2025 minus 90 multiplied by the number of times it went there. It went there 2 times. So we are seeing that every time we are squaring this, we are getting 45. Okay, so let's continue. What is 15 raised to 8? Again, it will be 45. The question was 15 raised to 2025. Is that okay? Mod 90. Yes. So then that means the first powering algorithm says we begin by 15, raise it to 1, see what we get. When we did that, we got 15. Then you square the first equation. That's 15 squared. And you told me it would be 225. Divide by 90 and record the remainder. So 90 into 225. Yes? 90 into 225, it went there 2 times. It went there 2 times. The remainder will be 45. Then you square this equation again. When you square this equation, you get 15 raised to 4. When you square 45, you get 45. That is mod 90. Again, do it another time. You get 45. Is that okay? So what I'm saying is, this 45 will persist. Every time I will be squaring, I'll be getting 45. So since it will persist, I want to stop at this point so that I don't continue squaring and squaring and squaring. Because I know I'll be getting the same thing. So let me, even from here, since I've discovered it will remain the same thing, from here, I can try to write this 2025 in terms of the power I have here. The power I have here is 2. So I want to see the relationship between 2 and this power using division algorithm. Is that okay? So by division algorithm, we know that 2025 the same as 2. How many times does 2 go into 2025? Just divide that by 2. And then not the remainder. You divide that by 2. 2025 divided by 2. Yeah? 10, 12. 10, 12. And the remainder is 1. The remainder is 1. Is that okay? Now, so what this means, I'm just trying to see if this will work. If it will not work, then we'll continue doing until we reach a number close to 2025. Is that okay? So what I'm imagining, therefore, is that if somebody gave me 15 raised to 2025, this person is the same as one who has given me 15 raised to 2 multiplied by 10, 12 plus 1. Because that is the same thing. Is that okay? And this is the same as 15 raised to 2, then raised to 10, 12, multiplied by 15 raised to 1. Because I've discovered every time I have this 15, if I have 3 squared, if I get 15, if I have 15 squared, it will give me 45. And then this 45, if I square it, it's just give me 45, 45. Every time I square it, is that okay? That is now the logic I'm using. Whatever is inside the bracket, 15 square is 45. This 45, you square it to give me 45. To give me 45. So if I raise it to anything, it will give me 45. So long as that thing is even, it will give me 45. And then times 15 raised to 1, which is 15. I just want to see, I don't want it to work. Let me see. This part, I'm assuming this part will give me 45. That's what I'm assuming. Then times 15. Let me see if it gives me. If it doesn't, then we'll have to redo. Okay, so this is, what is 45 times 15? 6 divided by 90. What is the remainder? The remainder is 45. Only divided by 90. It told me it was 675. 675 divided by 90, you get 7. Is that okay? So I now take that 675 minus 7 multiplied by 90 to get the remainder. Is it 45? The remainder. You know, if your calculator becomes very easy, like for me, if I have my calculator, I have this 675, then divide by 90, I get the result to be 7.5. So for me to get the remainder, I just need this 675 minus 90 times 7, because it went there 7 times. So if I multiply by 7, that gives me the remainder. Or relatively, just take whatever is inside on the right of the decimal and multiply by 90. That gives you the remainder. Yes. 52. When you have 675 minus 90, yes, minus 90 times 7. Getting 45. You see, I decided to stop at this point because that will have made our work easier. The other way would have been to continue squaring, as the first squaring algorithm says, continue squaring until you get this power or something slightly less than this power. And then you choose which ones you would sum up to give you 20, 25. Now, so I want to take that route, but before I take that route, I want to first of all confirm that you're getting 45 here. On you 675 divided by 90 is the remainder 45. It's 45, is that okay? So the remainder is 45. Yours is not. Let me see what you have in your calculator. Yes, what you're saying is, you see, you've done it well. You have 675 divided by 90. You have your answer 7 point. So 7.5 is the answer. So now what we do, take 675 minus the divisor, which is 90, times 7. So, yes, that is 675. 675. Because 7 is your result, the whole number 7. So ignore the decimal. Yes. Ignore the decimal and then tell us what you get. Because the decimal is talking about there's a remainder. It's telling us there's a remainder. That remainder is what we want to find out. What? 45, yes. So we used a shortcut. Let's now go the long way. Supposing you did not see this shortcut, because you may fail to see the shortcut. So if you fail to see the shortcut, then you just continue squaring. Is that okay? Continue squaring. So, but we've already realized that when you continue squaring, whatever we'll be getting is 45. So that makes our work even easier. So let's just continue squaring. Okay, so let's square. Now we had reached here. When you square this, you have 15 raised to 16. And 45 squared will give you again 45. Square that, you have 15 raised to 32. 45 squared will give you 45. Remember, we are doing it more than 90. So you're only writing the remainder. Is that okay? Square again, you have 15 raised to 64. And that squared will give us 45. Square again, you have 128. And that will give us 45. Square this, you have 128 times 2 is squaring. So that gives you 250, 256. And this one gives you 45. Square again, 256 times 2, that gives you 540. Is it 512? 512. And this gives you 45. Square again, 512 times 2, that gives you 1024. Is that 1024? And the square, the right side gives you what? 5. And let's see, if we square again, that will give us 2048. The power will be 2048. Which is beyond what we want. Is that okay? So so that means this is the last time we are squaring. So from here now we check which ones do we combine. Is that okay? So we check the ones we combine. That means now 15 raised to 2025 with the same as 15 raised to the highest power here, which is 1024, plus what? So what is left? When you subtract 1024 from 2025, what is left? Just subtract with your calculator. We have 2025 minus 1024. The remainder is 1001. We have such a power. We don't have, is that okay? So the closest we have is 512. So we add 512. 512. The power. So I don't have space. Let me just write here 512. So what is left? What is left? So in fact, instead of doing that, I just erase this and say times 15 raised to 512. Now, so what is left? we were left with 1001. We've taken care of 512. We are left with 489. The power of 489, we don't have it. The closest one we have is 256. So 15 times 2, 56. So that reduces to what? We are now left with the 233. Is it? We're left with the 233. The closest we have is 128. Let's reduce 128. We're left with 105. The closest we have is 64. So let's remove 64 from this. We are left with 41. The closest we have is 32. Let's get rid of 32, remove 32 from this. The closest we have is 9. Power 9. Power 9, no, we need the power 9. That's what the one we're left with. All we have is power 8. Is it? 15 power 8. So you're left with the 1. So the one we have is 15 raised to 1. So what you realize, if you add all these powers, it should give you 2025. Those powers, see, you see, it's good to confirm. 1024 plus 512 plus 256, 128, 64, 32, plus 8, plus 1. Yeah, we have 20, 25. So our power is okay. So we now multiply those numbers. This number here was 45. So that means 45 times this number here was again 45 times this number here was again 45 times this number 50 raised to 128 was again 45 times 50 raised to 64 was another 45. Is that okay? And then times 50 raised to 32. 50 raised to 32. What is that? It's another 45. 15 raised to 8. Another 45. Is that okay? Huh? How many 45s do you have? How many 45s do you have? 1. The one that is not 45, the only one that is not 45 is 15 raised to 1. The rest are 45. How many are they? 1, 2, 3, 4, 5, 6, 7. 7 of them. Is it? Are they 7? We have 7 45s. So you multiply all of them, then multiply by 15. Get the result. Can you calculate too? Calculate inafanya 15 times 7 inakataa. Inasema ni math error. That means the number is too big. So when the number is too big, now combine 45 mara mbili, get the result. Another 45 mara mbili, get the result. When the answer is too big. Is that okay? So we now combine because at times utafika mahali calculator ikatae kufanya because it's a big number. You combine. What we know is this. I know that if I have 2 times 7 times 3 times 4, I can do this, get 14. Then that 14 multiplied by this, get 42. Is that okay? Then that 42 multiplied by this. So I can do it bit by bit. It's not a must I should multiply 7, 2, 7, 21, and 4 at the same time. It's not a must. You can combine 2, get a result. Combine 2, get a result. Combine 2, get a result. Then multiply all these results. So what I mean is, if I have that, how many 45s did we have? There were 7. Is that okay? So we do all of them, but in pairs. In pairs, because your calculator cannot do that. But for us, we can do it. So what we have is 45 times 45 times 45 times 45. How many are these? 1, 2, 3, 4, 5, 6, 7, and the last one is 15. Eh? Now multiply these 2. What do you get? 125 mod 90. That gives you 45. So this 2 gives you 45. Is that okay? Yes. Now this 45 times this 45 mod 90. Another 45 now here. Is that okay? This 45 times this 45 mod 90 gives you 45. Is that okay? This 45 times this 45 mod 90 gives you 45. Is that okay? This 45 times this one mod 90 gives you 40. This 45 times this one mod 90 gives you 45. Now this 45 times 15. So you can see we've been reducing mod 90 as you move along. Otherwise, your calculator cannot do that. So you now have 45 times 15, which is 6.75. Is that okay? Mod 90, that gives you 45. So ukifika mahali kama hapa, you reach here, and your calculator cannot do it. You now do it, you pair them and do little by little as you progress. I think we can stop at that, unless somebody has a question. There's no questions, so I think we can stop at that. Thank you.
Thank you so much.